Welcome to section 8.7, day 2. We've already learned how to create a Taylor polynomial, a Maclaurin polynomial. Now we're going to talk about when we can use that created polynomial to approximate a value. So our first example here, they're going to ask us to use the Maclaurin polynomial to approximate the value of the natural log of 1.1. They're going to tell you what degree of the polynomial they want you to find. So they want us to find the fourth degree. So that means we're going to have to find the first derivative, second, third, and the fourth derivative. We already know that we're going to be working with the natural log. Now, if they ask us to find the approximate value of the natural log of 0.8, 0.1, 0.2, then we're going to use just plain ordinary natural log of x. But because they want 1.1, we're actually closer to the 1 than we are the 0. So finding the polynomial based on the natural log of x probably isn't our best bet. So we're going to use the natural log of x plus 1, as suggested right here. All right, so we're going to find our first derivative. So the original function is the natural log of 1 plus x. We're going to find the first derivative, which is 1 over 1 plus x. Then we're going to find the second derivative, which is negative 1 over x plus 1 squared. The third derivative, I'm going to try really hard to squeeze this all on here. That's going to be 2 over x plus 1 cubed. And then our fourth derivative, which is as far as we need to go. Make sure you put that 4 in parentheses so nobody thinks it's f to the fourth power. That's going to give me my negative 6 over x plus 1 to the fourth power. So whatever degree you're asked to find, you need to find that many derivatives. And then we need that value at 0 because this is a Maclaurin polynomial. So if I put 0 in there, I get 0. If I find the derivative at 0, that's going to be 1. The second derivative at 0, it's going to be negative 1. The third at 0 is going to be 2. And our fourth derivative at 0 is negative 6. So now we're ready to make our polynomial. And remember, we just put p and we put a little 4 there so people know. Alrighty, so remember, it is your function's value. Okay, and then plus, we take the derivative's value at 0 over 1 factorial, and then this would be x to the 1 power, plus the second derivative's value at 0 over 2 factorial x squared, plus the third derivative's value at 0 over 3 factorial x to the third, and then our fourth derivative's value at 0 over 4 factorial x to the fourth. Okay, and of course we'll want to simplify that all nice and pretty. So 0, of course 0, 1 divided by 1 factorial is just x. And then we have negative 1/2 x squared plus 1/3 x to the third minus 1/4 x to the fourth. Now, this is going to give me that value at 1. So if I want 1.1, I'm going to find that polynomial value at 0.1. Okay, because this already was at 1, because that's where we got the 1 plus x. So if I put 0.1 up into this function, so I'm literally taking 0.1 minus 1/2 times 0.1 squared plus 1/3 times 0.1 to the third minus 1/4 times 0.1 to the fourth. This approximation is going to be 0.095383. Okay, and if you used your handy dandy little calculator and just did the natural log of 1.1, so if we actually used our calculator just to see how close we got, we get 0.09531018. So look how close we are. We are accurate to right here. Okay, That's where we kind of drop off. So that fourth degree polynomial there wasn't too bad of an approximation. All right, so if they ask you to approximate a value, they're going to tell you the degree, so that's how many derivatives you have to do. So number of derivatives. Whatever they give you here, if it's 1 point something, 2 point something, you know you'll do 1 plus x, 2 plus x. So you're going to figure out these numbers based to how close you are. Okay, 1.1 was closer to 1 than it was to 0, closer to 1 than it is to 2. So that's why we have the 1 plus x. So to approximate a value, not too bad. Okay, now for, all right, no good way to do this. Now for the BC calculus, which is what this course is designed for, there's only so much time I have to teach you this information, so I really have to think about how much I can teach you and how many points that's going to give us on the AP test. I know that's kind of a bad way to think about it, but I want you to pass the AP test, so I'm trying to give you the best bang for your buck. This remainder, the error of the Taylor polynomial, is kind of difficult, so it may not give us the bang for our buck. So I'm going to try to make this as streamlined as I possibly can, try to make this as easy as I can. But please note, if you're thinking about a Calc 2 situation, you are going to need to go very deep into this. So I'm kind of doing the tip of the iceberg here. All right, so that error of your Taylor polynomial. If you use an approximation, you want to know how accurate it is. When we did this one, this is what we found, and this is what the calculator gave us. Okay, so there's a degree of accuracy that we have using our Maclaurin polynomial that we have a problem with versus the calculator. So there's an error here. We want to know what that error is. Okay, and so this is your original function. This is the function we're approximating. Okay, this is our Taylor polynomial. This is the function or the polynomial we are finding to approximate that value. This is the remainder, okay? That is that error. That's how much we're off by, okay? So when I look at that previous question, okay, this was my polynomial, okay, plus some remainder, that's going to give me this exact value. Okay, so 0.0953083 plus something is going to give me this guy. That would be my error. Okay, so that error is that absolute value of that remainder. All right, so Taylor's theorem. If a function f is differentiable through order n plus 1, in an interval I containing c, then for each x in I there exists a z between x and c such that, all right, sometimes I don't understand why they even give us these, they're just crazy. The key in this little phrase is that z is in between x and c. Okay, so that little sentence right there is our importance. Okay, now, remember that f of x is equal to your Taylor polynomial plus that remainder. Okay, so this right here, that is your Taylor polynomial. Okay, so that is our Taylor polynomial because there's our remainder. Okay, well that remainder is what I really want to find. Okay, so r sub n, that remainder, is going to be that next term in that Taylor polynomial. So see where we stopped here, okay? You're going to use f of n plus 1, so you'll have to find the next derivative of z, and remember, z is in between x and c, okay? C, remember, they'll tell us what that is, so like on a Maclaurin polynomial, that c is 0. And then n plus 1 factorial, and then times your x minus c to the n plus 1. So if I wanted to find the error in this polynomial that I did, see how this is a P4? This is a P4. My R sub n, I'm going to need to find that function's value at 5, because I'll put it over 5 factorial, and then that would be x to the 5th. So that remainder is going to be that next term. So if we have a 4, it's going to be 5s. Okay. All right. Z is in between x and c. This remainder, okay, is that Lagrange form of the remainder, Lagrange, okay? And then that absolute value of that remainder, okay, you've got your x minus c to the n plus 1 power over n plus 1 factorial, and then you've got that max. Okay, and you're going to see, we're going to do an example, and you're going to see where we want to think about how big that can be, okay, because we know our remainder will be equal to or less than. So it's kind of like we'll be looking at it and we'll kind of overshoot that, okay, going, hey, this is as big as it's ever going to be, so we know it will be bigger than that remainder. All right, it's clear as mud, I know it. All right, so here we go with our problem. Okay, they ask about the third Maclaurin polynomial for the sine of x. Okay, is given by, and we have found the Maclaurin polynomial for the sine of x. We know that it alternates. It's going to be those odd powers. We know cosine would be those even powers. Now they want us to use the Taylor theorem, okay, and that's just this guy right here, to approximate sine 0.1 by this function, or this polynomial, and determine the accuracy. Okay, so we already know what this Taylor polynomial is, or this Maclaurin polynomial is, but I know I'm going to need that accuracy, so I'm going to have to find that R sub n, which means I'm going to need to find the fourth derivative. Okay, so just to kind of refresh our memory here, our original function is sine, and I'm going to kind of streamline my notation here so I can fit it all on there. The first derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine. And then the fourth derivative, what I need for my error or my accuracy, is back to sine. Okay. So the first thing I need to do is look at that remainder, okay? And remember, this is your n, so this is your n. But in order to find that remainder, I've got to use the fourth term, so to speak, okay? So that's going to be my f of 4, and then z, okay, 4 factorial, x minus c. Okay, so that's my little formula here from that Taylor theorem. Okay, so all I've done is use this guy right here. Okay, so I just rewrote that little formula. I know that this was a 3, so 3 plus 1 is 4, blah, blah, blah. So that x minus c, I know that c is 0 because I'm actually working with a Taylor. I'm sorry, I'm actually working with Maclaurin, so that's how we know it's 0. Sorry, I'm trying to make this as easy as possible and I'm stumbling. Okay, so my derivatives value at z, okay, so remember here's my fourth. Okay, so I'm going to plug that in. And I need this of z, so I'm going to plug z's in for all of these signs. So I'm going to have sine of z. Everything else is going to stay the same, so I'm just going to make that substitution there. I've got 4 factorial, and then here, since c is 0 because it's a Maclaurin, that's just going to be times x to the 4th. Okay, so that is that remainder. Okay, so now I have to figure out the rest of it. Okay, All right, so when I look at my original function, I know that's going to be that polynomial plus that remainder. Okay. Okay, so I know my original function is sine of x. And I know that that third degree polynomial, they gave it to me right up here, which is x minus x to the third over 3 factorial, plus my remainder, which I just found, was sine of z all over 4 factorial x to the fourth. Okay. Now remember that z is in between your c and your x. It's in between x and c. Okay. So that means z is going to be in between 0 and 0.1. So 0 and 0.1. Okay. So with that Taylor polynomial, z is in between x and c, and you do want to write that in order. So that's where I got there's c and this is x. Okay. All right, so I am going to put in 0.1 for all of my x's here. I'm going to have to go to another slide because I'm running out of room. Okay, so that p sub 3 at 0.1. Okay, because remember, 0.1 is closer to 0. That's why we're using sine of x. So that means I'm approximating this guy. Okay, and I'm going to put 0.1 in for all of my x's. Okay, and I'm just putting in my 0.1 for all of those x's because they asked me to find the approximation first, then determine the accuracy. So if I put that 0.1 in, I've got x, which is 0.1, minus 0.1 to the third power divided by 3 factorial. Okay, so that is going to be approximately 0.099833. Okay, so the first part of what they asked me to find was to approximate sine of 0.1. Got it. Told me what to use, did it. Okay, and you could have done that right off the bat. Now, they want me to find that accuracy. So that's where I'm going to use that r sub 3 of 0.1. Okay, so that gives me sine of z over 4 factorial times x to the fourth, which is 0.1 to the fourth. Okay, and if you remember, okay, we want to maximize this guy right here. Okay, we've already used this part of our Taylor's polynomial. Now we need to think about that max. Okay, so when I'm thinking about that max, okay, I have got to think about how big my sine can be. Okay, so I know that I'm going to be, like what I'm putting right here, the sine of z, remember z is in between 0 and 0.1. Okay, and remember sine of z goes in between 1 and -1, so I know that sine of z has to be less than 1 because I would equal 1 if I could get up there to a whole number, but I'm at 0.1, so I'm not even anywhere close to being at 1. So I know this guy is going to be less than 1. Okay, and then you're going to multiply that by your 0.0001 over 4 factorial. So this guy right here, is this guy right here. He's going to be less than 1. Okay, this 4 factorial 0.01 to the fourth power, that's this guy right here. Let me see how many other colors I can get in here. That's that guy right there. Okay. All right. How super is that? All right. So when I look at this guy right here, I know that what I have right here for my r sub 3, okay, is going to be approximately, okay, all of this right here, 1 times 0.0001 divided by 4 factorial is 0.000004. Okay, so 1, 2, 3, 4, 5 zeros, got them. Alrighty, so I know that my answer, okay, is going to be in between, so this is P of 3, okay, this is the true answer, okay, and this is our P3 plus R3. Now my P3's value, remember, was 0.0099833, sine of 0.1, 0.0099833 plus 0.12. So my accuracy is pretty good. Okay. All right, so I know that is a huge amount of stuff to think about, okay? So really, the first thing you need to do is figure out how many derivatives you need to find so that you can find that remainder, that Lagrange member. Okay, so they tell me to use P sub 3, so I know I'm going to find R sub 3, which means I go up to the next term, so I'm up at 4, okay? Which means I'm going to use my sine of z over 4 factorial times x to the 4th. So it's just that next term, okay? So I literally found that 4th derivative, plugged z in for the x right there, because I don't know what that value is, okay? So they told me z. All I know is that z is in between 0 and 0.1. So I'll think about what that value is between 0 and 0.1. Estimate big so that I know my error is safely in between there. Okay, so they gave me the original, okay, 3rd term polynomial there. I find the next term up for the remainder. I put z in there for the x here. Okay, and then I shoot big. Okay, that sine of z, I know it's going to be, the biggest it's going to be ever is 1. Okay, so if I put the 1 in here, I can put the less than sign here safely, okay, because I know I've overshot it, okay. This value, I could find the exact value there, okay, so 1 times that is this guy, okay, and then once I have the estimation of the P3, this is the original, I know I'm in between that guy, P3 plus that remainder, so safely I'm in between there. So here is my accuracy, okay, which really isn't too bad. Okay. All right, so I will see you tomorrow at school. I know this is probably driving you crazy. We'll talk about it tomorrow. We'll see, you know, just how much we would have to find, because we're just going to try to get as many points on these problems as we can. We may, excuse me, we may not be able to get every point on this free response question, but we're going to get as many as we can. So we're going to talk about, gosh, how much of this am I going to have to do to get some points? We'll talk about that tomorrow. So do not fear, little ones. It will be